Hi calculus students! In this lesson we're moving on in Unit 1. Our previous topic in Unit 1 was limits, and now our next big topic is called continuity, which may sound a little bit familiar, but we're going to learn about it in the context of calculus. So this lesson is going to focus on exploring discontinuities. We're going to start off with a warm-up. So go ahead and pause me and spend about 5 minutes trying this warm-up on your own. You did it, right? You done? Okay. Here's my answers to the warm-up. So in the first problem, we were just looking at a graph, and we were asked to find the limit as x approaches -3 from the left, the right, and then just the general limit. So as x approaches -3 from the left, we can see that along the vertical asymptote, the function is going to positive infinity, and then from the right, the function travels along the vertical asymptote to positive infinity. So from the left and the right, it's going to positive infinity, which means that the limit overall is also going to positive infinity. So hopefully that one was pretty easy. 2 was a little bit more challenging. We had the algebraic limit. So if I'm trying to find the limit of f of x as x approaches 1, that means we're plugging in 1 into our limit. If you just try to plug in 1, you can see that I wrote here, you get 0 over 0. 0 over 0 is an indeterminate form. When we get that indeterminate form, it means we have to work on the function to be able to solve the limit. And so that's why I factored it. So you can see I factored it right there and canceled out this term x minus 1 because that is what gave us the issue with plugging in 1. So when I cancel out x minus 1, that means when I plug in 1, I'm no longer going to get 0 over 0. So then I just had the function 1 over x minus 3, and now when I plug in 1, I get -1/2. Okay. So hopefully this went pretty smoothly so that we can continue on with our lesson. Okay, just some quick review in the beginning, just to remind you about what discontinuous mean. So a function is continuous if it doesn't have any abrupt changes in value. And these abrupt changes in value are going to be called discontinuities, which is what we're focusing on for the rest of the lesson. A continuous graph is unbroken and you can draw it without lifting your pencil from the paper. So just to kind of exhibit this continuous function on the left, you can see if I wanted to draw it or highlight it, I don't have to lift up my pencil, and I can do that. Beautiful, continuous. However, the function on the right, if I try to draw this one, you can see right here there's an abrupt change in value where it kind of jumps up here, and I had to lift up my pencil, and then it goes down, then I have to lift up my pencil again to draw this little segment over there. So this is a not continuous function, and it has multiple discontinuities. You can see it had 2 discontinuities where I had to pick up my pencil. And we're going to be focusing on how to identify these discontinuities in a graph as well as in an equation. So, we have 3 types of discontinuities that we're going to be focusing on. The 3 types are called removable discontinuities. So that's right here, removable discontinuities, infinite discontinuities, and jump discontinuities. So you can go ahead and pause me as you take these notes. And now that you've finished copying down the notes, I want to comment on some of the specifics of each of these. So the removable discontinuity is what we call the graphs that have the holes in them. So we've seen these graphs before when we were solving limits. Sometimes the function results in a hole. We've seen that. And so that's what the hole looks like. It's called a removable discontinuity. And then I added this line down here just to kind of highlight a special characteristic of removable discontinuities, and that's that the limit from the left and the limit from the right are equal to each other. So the limit exists, there's just a hole at the point that makes it not continuous. Okay, so if I tried to draw this graph, I would have to lift it up at the hole to fill in that point, and then I'd lift up my pencil again to draw the bottom part. Over here we have a vertical asymptote in the graph, and the vertical asymptote results in an infinite discontinuity. I hope that makes sense. It just means at the vertical asymptote, the function is going to either positive infinity or negative infinity, so it's an infinite discontinuity. So if I tried to draw this, I'd get this left part, and then at the asymptote, I'd have to pick up my pencil to draw the bottom part. Then one maybe we're less familiar with is a jump discontinuity. So I kind of highlighted where the jump is. You can see that the left part of the graph has a completely different limit as x approaches c than the right part of the graph. So as the two different functions from the left and the right are approaching c, the limits are completely different. So that is like a big aspect of jumps, is that the limit from the left and the right are not the same, which can also happen with the vertical asymptote, but those are specifically going to infinity. And then before I move on from this, I just want to highlight or give examples of what you might see in an equation that will result in these types of graphs. So I hope it's pretty easy to like visually see, oh, well, removable discontinuity has a hole. Infinite discontinuity has a vertical asymptote. But more often than not, you're going to get an equation, and you'll have to figure out what type of discontinuities the equation will have. So I just wanted to give some examples. So one example is if I had g of x equals x minus 2 times x plus 5 over x minus 2. So in this equation, because I'm able to cancel or remove this term, so I'm canceling or removing this term, x minus 2, that will result in a hole. Or I don't want to say hole. I'm going to say removable discontinuity. At x equals 2. Okay, g of x has a removable discontinuity at x equals 2. Let's say our equation h of x is a little bit different. Maybe it's just x plus 5 over x minus 2. I am unable to remove the term x minus 2, which means the denominator will equal 0 when x equals 2. So there's a vertical asymptote at x equals 2, which means there is a infinite discontinuity at x equals 2. Okay, so these two you should be a little familiar with from our work with limits. And then this third type, a jump discontinuity. This is going to happen when you have piecewise functions. So you can see in the picture, it looks like they're two completely different functions, and that's because we might have something like j of x equals, let's say, x plus 5 when x is less than 2. And then we might have a different function like negative 1/2 x when x is greater than or equal to 2. So you can probably imagine those are two lines, but they're two lines that aren't ever going to meet. So some piecewise functions are nice where they touch and then those would be a continuous piecewise function. But these are completely different lines that aren't going to touch each other. So there would be a jump there. So j of x has a jump discontinuity. Sorry, my handwriting. At x equals 2. And then the other type, there is one other type of function other than piecewise, and that will be like some absolute value functions. And one example of an absolute value would be like, this is a really specific one, and I'll show you an example of that later. But the way that this absolute value affects the graph creates a jump in it. And I'll show you an example.